Look at your coffee for a second. Stir it with a spoon, stop and watch. The surface keeps moving. The liquid keeps turning even after your hand is gone. Now look bigger. The earth is spinning. The moon goes around the earth goes around the sun goes around the center of the Milky Way. The Milky Way itself is rotating, disks, rings, spirals, whirling clouds of gas, planets with days, stars with star spots that come and go because the whole star is turning. And the question sounds almost childish until you realize it's everywhere. Why is so much of the universe spinning? Because in everyday life, spinning doesn't happen by accident. You have to twist something. You have to apply a torque. You spin a top by flicking it. You spin a chair by pushing with your foot. You spin a wheel by turning an axle. Spinning feels like something you have to actively do. So what flicked the earth? What twisted the sun? What spun up entire galaxies? If you're hoping for a single dramatic cause, like a force of spin, I have bad news. There isn't one. The real reason is both simpler and deeper. It's not that the universe has a special spinning engine. It's that once you understand one conserved quantity, angular momentum, you start seeing rotation as the default outcome of how matter clumps, collides, and collapses. Let me build it from the beginning with a thing you can feel in your hands. Sit on a swivel chair, if you have one. Hold a couple of heavy books, one in each hand. Stretch your arms out and spin gently. Now pull the books inward toward your chest. You speed up. You didn't add any extra push after you started. You didn't touch the floor. You didn't secretly use a motor. You just changed your shape, and yet the rotation rate increased. That is the whole story, if you take it seriously. The rule behind it is called conservation of angular momentum. And the easiest way to say it is, if nothing external is twisting a system, then its total amount of rotation can't just disappear or appear. It can move around inside the system, it can shift between parts, but the total stays the same. In symbols, people write L, I-O-L, I-O. You don't have to love the symbols. The idea is what matters. LL is angular momentum. II is rotational inertia, basically how spread out the mass is. And OO is the spin rate. If LL is fixed and you reduce II by pulling mass closer to the axis, OO must increase. That's what you just did with the books. So now imagine something much bigger than you on a chair. Imagine a giant cloud of gas in space, not a neat sphere, a messy, turbulent cloud. Bits of it are moving in different directions because space isn't quiet. Gas has pressure. It has random motion. Nearby clouds pull on it. It gets stirred by shock waves from old supernovas. It's lumpy. It's noisy. Now here's the part most people miss. The cloud does not need to be perfectly rotating to have angular momentum. It only needs the tiniest imbalance, the tiniest swirl, and it will have one because perfect cancellation is not what nature usually gives you. Take a crowd of people walking randomly in a plaza. On average, the crowd might not be going anywhere, but pick any region inside that crowd, some patch, and you'll find a small net motion, a drift, a tendency, not because someone planned it, but because randomness doesn't cancel perfectly at every scale. A gas cloud is like that, but with gravity as the accountant keeping track. Gravity starts to pull the cloud inward. The cloud begins to collapse. Not instantly, not all at once, but gradually as denser regions pull in more gas. As it collapses, its size shrinks. Its moment of inertia, II, shrinks. And so the rotation rate, OO, increases. The small, almost unnoticeable swirl becomes a noticeable rotation. The rotation becomes a disk. The disk becomes a star system. This is why spinning shows up so often. Collapse turns tiny rotation into big rotation. You can demonstrate the same idea without a chair. Think of an ice skater pulling arms in. Or think of a spinning pizza dough. The dough starts wide, slow. Then it stretches and thins, and the distribution changes, and the spin changes. Anytime mass moves inward or outward while angular momentum is conserved, the rotation rate responds. So the first answer to why is everything spinning is because things are collapsing and clumping, and angular momentum is conserved. But you might push back and say, wait, why did the cloud have any rotation at all? Why wasn't it exactly zero? In a strictly mathematical sense, you can create a perfectly non-rotating collapse if you prepare initial conditions with perfect symmetry. But the universe is not a laboratory where someone sets initial conditions with infinite precision. The universe is messy. There is always some asymmetry, some nearby gravitational pull, some turbulence, some collision, some tiny net torque from the environment. And even if you had a giant region with exactly zero total angular momentum, you could still have parts of it spinning in opposite directions, canceling out in the total. Total can be zero while local rotation is everywhere. No net spin does not mean no spinning. Now let's make this more concrete with the most familiar spinning object you know, Earth. The Earth spins because the material that formed the Earth had angular momentum. That angular momentum was inherited from the protoplanetary disk, the disk of gas and dust orbiting the young sun. That disk existed because the original cloud that made the sun had angular momentum, and during collapse, it spun up and flattened into a disk. Disks are what rotating collapse makes, because rotation resists collapse most strongly in the direction perpendicular to the rotation axis. The system can fall inward along the axis more easily than it can fall inward through the equatorial plane. So you naturally get a flattened structure. Inside that disk, dust grains collide and stick. Pebbles become boulders. Boulders become planetesimals. Planetesimals become protoplanets. Every collision carries angular momentum. Some impacts spin the growing planet faster. Some slow it down. Some tilt it. Some flip it. That's why planets have different day lengths and different tilts. It's not that every planet is politely rotating the same way. It's a record of formation history, collisions, accretion, and gravitational interactions. Earth's tilt probably owes a lot to big impacts early on. Uranus is tilted on its side, likely from a colossal collision. Venus spins very slowly and backwards compared to most planets, possibly from impacts and tidal effects and atmospheric interactions. The point is, once you allow collisions in a rotating disk, you almost can't avoid spin. You would have to carefully arrange impacts to cancel it out again and again with absurd precision. Now you might notice something else. The Earth spins, but it's also slowing down very gradually. Days get longer over geological time. Why? If angular momentum is conserved, how can spin slow? Because angular momentum can move from one place to another. Earth's spin angular momentum is being transferred to the Moon's orbital angular momentum through tides. The Moon raises tidal bulges on Earth. Because Earth rotates faster than the Moon orbits, those bulges are pulled slightly ahead. Gravity between the bulge and the Moon acts like a torque. It drags Earth's rotation down and pushes the Moon outward. The Moon slowly recedes. Earth's day slowly lengthens. Nothing violates conservation. The angular momentum isn't vanishing. It's being redistributed. This is a theme. When you see a spin change, look for where the angular momentum went. Now jump back to the star-forming cloud, because here we hit a problem that sounds technical, but is actually the key to why planets exist at all. If a collapsing gas cloud conserves angular momentum, it should spin up so much that it can't collapse into a compact star. The rotation would get too fast, and centrifugal effects would prevent further collapse. Yet stars do form, so the system must shed or move angular momentum outward during collapse. How does it do that? Through disks, friction, magnetic fields, and outflows. A rotating disk is not a perfectly frictionless set of rings. The gas has viscosity and turbulence. Different rings interact. Magnetic fields thread the plasma. These effects allow angular momentum to be transported outward. Inner parts lose angular momentum and fall inward to feed the star. Outer parts gain angular momentum and move outward. And along the way, many systems launch jets and winds, material blasted out along the rotation axis that carry away angular momentum. So the star can form in the center while the disk remains around it, and that disk is where planets can form. This is why you see disks everywhere. around young stars, around black holes, around forming planets. Disks are nature's way of managing angular momentum while letting matter fall deeper into gravity's well. Now scale up again, galaxies. Galaxies are not solid wheels, but many galaxies do have net rotation, and some form beautiful spiral patterns. Where does that rotation come from? Partly from the same principle, collapse and conservation. A proto-galactic cloud collapses under gravity. Any small net angular momentum gets amplified as the cloud shrinks. But galaxies also gain angular momentum from gravitational interactions with their neighbors during formation. In the early universe, matter was not uniform. It had slight density variations. Regions pulled on each other. Those gravitational pulls exerted torques over long times. This process, called tidal torquing, can spin up forming halos. Later, mergers between galaxies can add or rearrange angular momentum dramatically. A galaxy's rotation can be seen as a fossil record of the torques and mergers in its past. And again, you don't need a special spin force. You need two things: gravity to clump matter and a conservation law that turns small imbalances into rotation as size decreases. At this point, you might ask a more philosophical question: why is angular momentum conserved in the first place? This is where physics gets beautifully strict. Angular momentum conservation is not an arbitrary rule somebody wrote down. It follows from a deep symmetry. The laws of physics don't care which direction you face. If you rotate your whole experiment in space and run it again, the outcomes are the same. No direction in empty space is special. This rotational symmetry implies a conserved quantity. That connection between symmetry and conservation is one of the deepest ideas in physics. So if the laws are rotationally symmetric, angular momentum conservation isn't optional. It's built in. Now you might think this still doesn't answer your original intuition, but spinning needs a cause. It does. The cause is torque. But torque doesn't need to be dramatic or singular. It can be tiny and cumulative. It can be random and statistical. It can come from asymmetry in a collapsing cloud, from nearby masses pulling unevenly, from collisions that don't line up perfectly, from turbulence, from gravitational interactions over millions of years. And here's a critical point. It's actually harder to make a universe where nothing spins than to make one where lots of things spin. Because no spin anywhere requires perfect cancellations everywhere. Nature doesn't do that unless forced by a symmetry, and the early universe had fluctuations. Those fluctuations are the seeds of everything: stars, galaxies, you. Fluctuations mean a symmetry. A symmetry plus gravity plus conservation means rotation. Now let's talk about something that seems like an exception. Why isn't everything spinning insanely fast? If collapse speeds spin up, shouldn't things reach ridiculous rotation rates? Some do. Neutron stars can spin many times per second. Some pulsars spin hundreds of times per second. That's the ice skater effect taken to an extreme. A massive star's core collapses from a huge radius down to something like a city size. The moment of inertia collapses, the spin rate explodes upward. But even there, physics has brakes. Magnetic fields can radiate energy away. Neutron stars can lose rotational energy through electromagnetic radiation and particle winds. They can also lose energy through gravitational waves if they have asymmetries. Again, angular momentum and energy move around. For planets and stars, there are also limits. If a body spins too fast, it can deform, shed mass, or break apart. There is a breakup speed where centrifugal effects at the equator compete with gravity, so objects can't spin arbitrarily fast and remain intact. Now there's a second meaning of spin in physics that can confuse people: quantum spin. Electrons have spin, protons have spin, even photons have a kind of angular momentum. This is not a tiny literal ball spinning. It's a quantum property with angular momentum-like behavior built into how particles transform under rotations. It's another place where rotational symmetry shows up. In quantum mechanics, rotation is not just a motion, it's a transformation of the state. Particles can carry intrinsic angular momentum as a fundamental property. So when you say everything is spinning, you can mean two different things. Macroscopic rotation, like a planet turning, and intrinsic quantum spin, like an electron. Both connect back to rotational symmetry, but they are not the same physical picture. Now let's bring it back to your everyday world, because this is where the intuition rewires. When you see a spinning planet, you might imagine someone had to start it like a toy top. But planets are not toys placed gently on a table. They are the product of a violent, chaotic formation process where billions of collisions occurred in a rotating disk. Spin is the statistical outcome. When you see a spinning star, you might imagine the star choosing to rotate. But the star is the center of a collapsing cloud that had angular momentum and had to manage it. Rotation is the bookkeeping. When you see a rotating galaxy, you might imagine a cosmic motor, but galaxies form from clumping matter and torques from neighbors. Rotation is the fossil record. And when you understand that, you stop thinking of spinning as an extra feature. You start thinking of it as a consequence of two facts. Gravity clumps and angular momentum doesn't vanish. There's another subtlety that's worth saying out loud, because it's where people often get misled by dramatic titles. Not everything in the universe is spinning in the same direction. Not everything is a neat rotating disk. Some objects tumble. Some are chaotic. Some have very little net spin. Some systems have angular momentum that cancels out in the total. The universe isn't one giant whirlpool. What is true is this. In a universe with matter, gravity, and small asymmetries, rotation is incredibly common because it is hard to get rid of angular momentum, and collapse amplifies whatever you have. So the mind-blowing truth is not that the universe contains a secret spinning force. The truth is that rotation is what you should expect when you have symmetric laws, conserved quantities, and clumping. And now, the last step, why should you care? Because angular momentum is one of those ideas that once you learn it, you see it everywhere. It explains why a skater speeds up. It explains why hurricanes rotate, and why they rotate in opposite hemispheres because of Earth's rotation and the Coriolis effect. It explains why accretion disks form. It explains why binary stars exchange angular momentum. It explains why tidal locking happens, why the moon always shows one face, why close-in exoplanets often show the same side to their stars. It explains why pulsars can be cosmic clocks. It's a single idea that keeps paying rent across scales. So the next time someone says, "Why is everything spinning?" you can give a simple answer that is actually correct. Because most large things formed by gravitational collapse from messy initial conditions, and angular momentum is conserved. So as things shrink, they spin up. And whatever angular momentum can't vanish must be carried somewhere. Into disks, into orbits, into jets, into radiation. And if they push and say, "But why is angular momentum conserved?" you can give the deep answer, because the laws of physics do not pick a preferred direction in space. Rotation symmetry forces conservation. And if they push again and say, "Why is the universe symmetric that way?" you can be honest. That's part of the structure of the world we observe. We don't start from comfort. We start from patterns, and we discover the rules that match them. The universe is not obligated to feel intuitive, but it is consistent. And consistency is enough to build understanding. Now go back to the magnets, the table, the spinning coffee, the planets, the galaxies. It's the same kind of lesson each time. Your intuition is tuned to human scale, but the universe is tuned to principles. Once you learn the principles, the weirdness doesn't vanish. It moves. It becomes a different kind of wonder. Not, "How is this possible?" but "Of course it's this way. How could it be otherwise?" That is the real payoff. And the next time you look up at the night sky, remember, you're not looking at a still picture. You're looking at a universe that is constantly trading angular momentum between clouds, disks, stars, planets, and galaxies, shaping structure, creating stability, and writing history in rotation.